Hello, everyone, and a very warm welcome to Kognito Key. I am absolutely thrilled to have you here today. In this explainer, we are going to dive into a truly fascinating topic: how exactly our computers handle the intense demands placed on their incredibly limited memory. Let's jump right in and explore a brilliant behind-the-scenes mechanism in operating systems called swapping. Section 1. The main memory problem.
To really understand the solution, we first need to understand the problem, right? For any process to actually execute, it must be placed directly into your main memory, your RAM. But physical RAM is severely limited. Just think about the number 500 for a second. Today, a single user application can take about 500 megabytes of memory space just to start up. Imagine what happens when you open just a few browser tabs. The very moment your system boots up, 50 to 100 background processes instantly start running, eating up 5 to 10 megabytes each, and that's all before you've even clicked a single icon. Increasing RAM size endlessly would just skyrocket the cost of our systems, so the operating system needs a really clever workaround.
And that brings us to our hero of the day, swapping. Swapping is this highly cost-effective memory management method. Honestly, you can think of it like a high-speed traffic controller for your memory. When the main memory gets completely full, the operating system grabs an idle or blocked process and temporarily moves it out of the RAM and onto the backing store, which is your disk. This instantly frees up space, allowing a ready process to take its place and execute.
This builds into a continuous, lightning-fast cycle. Step 1, a running process gets blocked because it's waiting for something, maybe a user input. Step 2, the memory manager immediately swaps out that blocked process straight to the disk. Step 3, it swaps in a process that is fully ready for execution. The real beauty here is that the memory manager swaps these processes so incredibly fast, the CPU always has something ready to execute. Literally, no time is wasted.
But how does the system actually choose who gets to stay in the RAM? Well, it relies on priority-based preemptive scheduling. Imagine a highly important process suddenly arrives on the scene. The memory manager will preemptively grab the process with the absolute lowest priority and send it to the disk. Once the high-priority superstar finishes its job, that lower-priority process is swapped right back in to continue executing. In the computer science world, this specific variant of swapping is famously known as rollout, roll-in. So, all of this moving back and forth raises a pretty crucial technical question. When a process is swapped out to the disk and then swapped back in again, does it occupy the exact same physical memory address it had before? What do you think?
Well, the answer actually completely depends on your system's address binding technique. If your system uses static binding, where addresses are strictly set during compiling or loading, it's very difficult to relocate the process. It basically expects its old spot back. However, if the system uses execution time binding, those physical addresses are calculated on the fly during execution. This means the process can be seamlessly swapped into a completely new location in the memory without any issues at all.
Section 2. Where does it go? Backing storage.
We've talked a lot about the main memory side of things, but where do these massive process images actually go when they get kicked out of the RAM? They head to the backing storage, our hard disk, which obviously must have enough space to accommodate them. The operating system generally has two alternatives for organizing this on the disk. The first is creating a separate swap file for each individual process, but watch out because this increases directory entries and really slows down search times for input and output operations. The second, much more efficient alternative is creating one giant common swap file. The system just estimates the size initially and then tracks the specific location of each process image within that single file.
Now, constantly swapping processes of different sizes in and out naturally leaves these fragmented holes of empty space scattered all throughout your memory. You might be thinking, why not just push everything together? Well, that is called memory compaction. You shift all active processes downwards to combine those holes into one large usable block. But typically, operating systems avoid doing this because physically shifting all those active processes consumes way too much valuable CPU time.
Because we try so hard to avoid compaction, we face one final technical hurdle. How much memory space should the operating system actually allocate to a process when it is created or swapped back into the main memory? The OS essentially has to anticipate the future. If a process is created with a fixed size that will never ever change, it's easy. The OS allocates the exact amount of memory space, no more, no less. But if a process has a data segment that is expected to grow while running, the OS smartly adds a little extra space, a bit of padding while swapping it in.
This prevents the massive overhead of having to shift the whole process to a totally new location later just because it got a little bit bigger. To sum it all up, swapping is the ultimate lifesaver that kicks in when our main memory reaches a critically low point, seamlessly shuffling processes to the disk and back so you can keep working without a hitch. But here is a provocative thought to leave you with. As solid-state drives become almost as fast as RAM, will we even need swapping in the future? Will the line between disk and memory just disappear entirely? If you loved this explainer and found it helpful, please make sure to subscribe to the Kognito Key channel, hit that like button, and share it with your friends and fellow learners. Until next time, keep learning and keep exploring.